The broadcast is now starting. All attendees are in listen-only mode.
Yes, good day. This is Dan Davidson, and I'm a consultant with the Illinois Soybean Association. And on behalf of the association, I want to thank you for taking time to come on to this webinar today, managing potassium and phosphorus for soybeans by soil test level, yield expectation, and water quality. Dr. Mullen works for Potash Corporation, soon to be merged with Agrium. Will be our presenter today, longtime soil fertility expert, specialist, got his Ph.D. at Ohio State, his Ph.D. in Oklahoma, and then worked at Ohio State, and now moved on to Potash Corporation to continue his work in soil fertility. Just a few housekeeping details for today. If you were CCA and you registered, you provided your CCA number, and you'll receive 1 credit in nutrient management for attending today. And if you need to attend the whole event to get the 1 CEU for nutrient management. If you're listening to this recorded version of this webinar at a later date, there is a CEU attached to this, nutrient management. You can go into your CCA account at the American Society of Agronomy, and you can self-apply for a credit, 1 credit. This webinar will be posted to a YouTube channel on the ILSO Advisor, as well as on Potash Corp's website as well. In a moment, I'll turn it over to Dr. Mullen to do his presentation. He will go ahead and present. Submit your questions in the little box on the dashboard. And at the end of his presentation, I will provide those questions to Dr. Mullen, and he can answer them. Again, on behalf of the Illinois Soybean Association, I want to thank Potash Corp and Dr. Mullen for making this presentation, and thank the attendees for coming along today. And Robert, I turn it over to you.
Well, thank you, Dan, and I'm also appreciative of the Illinois Soybean Association for the opportunity to spend an hour with you folks this morning. Going to be talking about managing potassium and phosphorus for soybeans. When Dan originally pitched this idea for having this conversation this morning, the title was Managing P and K. I do work for Potash Corp. Our primary nutrient is potassium, but we are also a fairly large phosphorus supplier. But we've been sort of running a campaign talking about changing the old traditional way of looking at fertilizers from NPK to NKP, and there's a lot of reasons for that. I won't go into those today, but so I sort of switched around the title on you for this particular conversation. I am a recovering academic, as Dan mentioned, so I did have 7 years at Ohio State University. I'm still fairly analytical, so a lot of what you're going to be seeing today, I'm not a huge fan of text on slides. Sometimes that can't be avoided, but I really rely much more heavily upon the use of graphics to sort of bring my point across. And so what you're going to be seeing a lot of today is a lot of data slides. A couple of them are going to be fairly intensive. I will do my best to walk through each one of those slides and provide a really good description of what you're seeing and how that impacts us as agronomists and impacts the way we should be managing nutrient inputs into our crop production systems. With that, I always kick off with an overview just to sort of give you a little bit of a template and some guidance as to what we are going to be talking about today. I know everyone out there is a huge fan of chemistry. I assume that because I am. So I will give you just a little bit of a chemical background of how phosphorus and potassium behave in soil. I think that's an important place to start when we're talking about managing nutrient inputs, specifically these two, where we do rely so heavily upon soil analysis as one of the primary tools that we have in our toolbox for making decisions. The goal is not to overwhelm you with the chemistry. The goal is not to make you a chemist. The goal is just to give you an appreciation of our understanding of what actually happens in the soil, and then how do we manage it, because that's ultimately what we're trying to do from that agronomic perspective is how do I capture information and translate that into a decision. And then also I'm really big on when it comes to showing you data, I like to show you the good, the bad, and the ugly. I like to show you what we think we have a really good understanding of, Where we have some knowledge gaps, some things we're less clear about, and then even more specifically about some of the challenges of collecting information, and how does that impact some of the uncertainty as it relates to making a decision. So you're going to get some of that today as well. So, and some of that's going to come in on the chemistry. Some of this is when I transition, when we start talking about rates. So we are going to cover just how does soil testing actually work, and then translating that into a rate decisions. How do we go from collecting soil test information, what's done at the university level to help provide some guidance and some guidelines for making nutrient rate decisions. And then something we're really big on, something I've been big on since I left academia in 2011, is developing economic models. Because at the end of the day, when we're talking to a farmer, I'm assuming a lot of the individuals on the call listening this morning are probably consultants to some degree and interacting with farmers. How do we bring this agronomic information into an economic decision tool? And we've spent a lot of time doing that at Potash Corp here the last 6 years. Some of that information is available on the website. That'll be presented at the very end of the presentation. But it's taking the agronomic information that we have and plugging it into an economic model. The one thing I will say about a lot of the information that I am presenting today, almost everything that we provide on our website and almost everything that I use when I'm building my presentations does come from land-grant university research. And there are some challenges associated with that, and I'll be walking through some of those today. It's still our best source of information. There's always some level of disagreement with regard to the recommendations that they do provide, and I'm okay with that, to be really honest with you. It's more than perfectly okay to challenge those scientists as they're conducting their research to make sure that they're keeping an eye and maintaining an interest in farmer profitability and farmer keeping him economically viable. And again, I'll be sharing some of those challenges exist. Again, I'm the guy that's going to tell you the good, the bad, and the ugly. Whether some people don't appreciate that, but that's just the way I operate. And then finally, as we think about for our nutrient management, which is really big right now in the nutrient management space, I'm obviously going to be talking about rates. I'm not going to talk too much about source. There will be some of that embedded at one of my last slides. But when it comes to managing loss, which is when we start thinking about water quality, that's really what we're talking about, is how do I manage my nutrient inputs in such a way to obviously, number one, maximize the agronomic benefit, which is hopefully going to translate into a maximized economic benefit. But then also, how do I manage that to minimize the environmental impact of my production system? And we're going to spend quite a bit of time talking about that. And what we're really going to focus on is timing and placement. And I tend to focus more on placement than timing. Timing is certainly a consideration, but if we can do a fairly good job with placement, I'm not saying that timing isn't important, but it becomes less important. So that's where we're going to finish up. We're going to have quite a bit of data slides, and really what it's going to come down to is how do I manage my phosphorus inputs in such a way to mitigate the risk of transport, and that's where we're going to wrap up this morning. So kicking off with potassium and phosphorus chemistry, we're going to start with potassium. And again, the goal here is not to overwhelm you with information. This is a fairly basic illustration of just what's going on in the soil, and do realize these are static representations of a very dynamic system. So the system is always in flux. Ultimately, for our desire as agronomists, what we're ultimately trying to do is we're trying to maximize the amount of potassium that is in solution that is ultimately available to a plant. At the end of the day, that's really what we're trying to do. Now, there are some pathways that we have to deal with, and some important things that we need to understand with regard to what goes on in the soil. We're going to talk a little bit about exchangeable K, because when it comes down to what the information we're capturing from soil testing, this is a very important player. This is actually what we're attempting to measure, because this exchangeable K can be readily desorbed to resupply any potassium in solution that's being removed by the plant. So we need to have some metric or measure of just how much exchangeable K is in that soil. And again, that's the primary basis for soil sampling and the use of the reagents that we use in a lab to provide us estimates of that value. The non-exchangeable fraction, this is sort of a newer area of interest, because we do occasionally conduct field experimentations on soils where we would expect a fairly large response to potassium, and we don't always see it. The exchangeable K would tell us there's just not much there, but when we conduct, let's say we're conducting a field experiment, we're having multiple rates of potassium on top of whatever the control is, and we don't see much of a response in yield relative to the control. Some of that can be explained by weather. That's obviously one of our bigger factors that actually impacts this dynamic system that we're talking about here. But there's also this non-exchangeable fraction that in certain situations can be a fairly significant source of potassium. We don't currently have a reliable way of measuring that terribly accurately. There's been a lot of different approaches that have been used to try to get a better handle on this particular fraction. But to date, from the scientific community, we just haven't come up with a really good approach. But that work continues. And then ultimately, the primary source of the potassium that we have in our soils is primarily locked away in a primary or secondary mineral. Feldspars are fairly potassium-rich minerals that exist within our soils, and we have our layer silicates. That's going to be our biotites and our micas. And they can be a fairly significant source of potassium. As I often say, the problem is with so many of these primary minerals, the amount that's actually weathered and released in any given production year is so small that we don't really concern ourselves with trying to measure it. And just to give you an illustration, I do try to provide some magnitude of scale of how much potassium is in solution, and then compare that to how much total potassium there is in a typical soil in the Midwest. So the total K in our soils can be anywhere from 10 to 50,000 pounds per acre. The problem with that is 99.9% of that, actually a higher percentage than that, isn't necessarily available to the plant. So we focus the bulk of our time. We don't really measure solution K, although we can. We're primarily focused on measuring exchangeable K. And just to make this a little bit more complicated, and again, the goal is not to make you a chemist or to make you a clay mineralogist or a pedologist, but this is ultimately what's going on within our soils. Is we have these clay structures. This is a representative of a 2-to-1 clay. We've got potassium, we've got calcium, we've got hydrogen, manganese, aluminum. This is our cation exchange capacity. When we're going in and we're attempting to measure exchangeable K, this is the fraction of potassium that we're trying to measure. We're going to capture what is in soil solution. As you could tell from the previous slide, the concentrations are fairly low. So what we're ultimately interested in is just what resides on the surface of these clays that can then replace anything that's being removed from soil solution. So our goal with fertilization is to ensure that we have an adequate amount of potassium residing on this exchange complex, so that as that plant is taking up potassium, something is there readily available to resupply what's being removed. There's a lot in this slide, but that's all we're really going to take away from this particular informational piece. So what do we actually do when we conduct soil sampling and submit that sample to a lab? What do the lab folks do with that? We flood that system with ammonium. That's going to displace all of the potassium that's held on those exchange sites. And we're going to use an ICP. We could do this colorimetrically. Actually, not colorimetrically. We can do it with an AA. We can actually measure the potassium concentration in our sample, and that gives us an estimate of exchangeable K within that soil. And then ultimately, as a scientist, what we're trying to do is, okay, what does that tell me specifically about crop response? There's a lot of other information that we capture down this path, but I'm going to take us right to the end point. And what we end up, and all I'm going to talk about today is the soybean. The reason the corn is here is just because this was the image that I had, and so I didn't want to separate out the two because I have to re-explain all the missing information. So what we have here is soil test K on our x-axis. We have relative yield on the y, which is the predominant way in which we present this type of information, and we develop a scatter diagram. And what we're trying to determine is at what soil test level, at what soil test level do I minimize the risk of having a yield decrease due to inadequate potassium supply. So the first thing you probably notice from these scatter diagrams is not all of the data below where we establish a critical level is below the 100% relative yield. There are some sites, some experimental locations where we don't see much of a response to additional potassium. And again, that comes back to that non-exchangeable fraction. It's also influenced by the production environment. If we have a really, really low yield environment, typically precludes the need for much fertilization. And then conversely, we see that also in the really, really high production environments. And again, I usually sort of walk you through the mechanism of just how does non-exchangeable K move its way into soil solution to supply crop demand. I didn't want to walk you through that this morning, but that information does exist, and I can provide that for additional contextual information if you're really interested. But this is what we're trying to do, and so what we learn is that, boy, you know, somewhere around that 200 part per million soil test level. Now, this is data coming out of Iowa State University from Dr. Mallarino's lab. Somewhere around that 200 part per million, the risk of having a yield loss due to inadequate supply is pretty low. And so that is one of the guidelines we use for establishment of a critical level. So our goal is ideally to try to achieve a soil test level that approximates that. And in that production environment, we would suspect that there would be very little risk of having a yield loss because of inadequate potassium. Again, this is not a perfect system, and I'll step through this when we start talking about rate decisions. There is some uncertainty, and you can probably recognize that just from looking at the scatter diagram here. There is some uncertainty. The question becomes, how do we manage that uncertainty? And we will talk about that moving forward. So this is sort of the first step, and this is what when we're doing experimentation, to provide better recommendations and guidelines for you, the consultant or the retail agronomist working with the farmer. This is sort of the first step, and we do use this as a way to identify critical levels. Phosphorus behavior in soil is a little bit more complicated. Potassium is fairly straightforward. Potassium is a lot more involved chemically. Primarily has to do with its lack of desire to be in solution. As you recognize, the concentrations in solution of phosphorus that we have to achieve to ensure we have an adequate supply for a growing plant are fairly small, where potassium was 1 to 10 part per million. Solution phosphorus is typically less than 0.3 part per million. Part of that is driven by just because of the chemical nature of phosphorus. It does not desire to be in soil solution. Just like we had for potassium, we have this adsorbed fraction of phosphorus. We don't call it exchangeable. Part of that is because of the chemistry. This is an adsorbed fraction. I've got a slide here in a moment that will sort of show what that actually looks like chemically. But some of that material can desorb, and as the plant is removing phosphorus from solution, it can desorb and resupply. Part of the challenge is whenever we supply fertilizer, a lot of the fertilizer that we supply gets sucked up into adsorption. It's going to be stuck on a clay edge or on the edge of a mineral. We can get precipitation. We can form iron, aluminum phosphates, calcium phosphates, driven primarily by pH. And again, all of these reactions occur with phosphorus, making it a little bit more challenging to ensure that we have an adequate supply in soil solution. We do have primary minerals that are our primary source of phosphorus in soil. The problem is their dissolution is fairly slow. A lot of that is driven by soil pH, but for all intents and purposes, we never attempt to measure this fraction, primarily because the dissolution of this fraction is fairly slow. Just like with potassium, the total amount of phosphorus that we have in our soil can be quite large. I've actually seen some soils here in central Ohio that are closer to 5,000 pounds per acre. The challenge is 99.99% of the phosphorus that is locked in our soil is not in a form that the plant is ultimately going to be able to access. And again, that necessitates the need for fertilization. This is why companies like Potash Corp do exist. We also have this organic fraction that we didn't have for potassium. So we do get mineralization and mobilization just like we get with nitrogen. It's not to the same degree. If you consider the C to N to P to sulfur ratio, the actual amount of phosphorus contained in our organic fraction is fairly small. And then once it is mineralized, it becomes a slave to these chemical reactions that are also occurring. So I have never seen a recommendation algorithm that takes this into direct account for when submitting and looking at organic fraction and then saying, well, this is how much phosphorus we would expect from that source. We do that for manure for obvious reasons, because we're treating it like a fertilizer source, but we don't measure organic matter in soil specifically to help us get a better rate decision on phosphorus when it comes to making a fertilizer decision. Just really quickly, and again, my goal is not to make you a chemist. My goal is just to sort of expose you to what's actually going on. We have this fixed phosphate, so this is an amorphous aluminum oxide edge, which is basically a clay. And if we get this double bonded oxygen feature, where we got it, that oxygen is bound, that oxygen is bound, this is what we call fixed. This material is not going to easily desorb from this clay edge. I usually talk about hysteresis, which is a basic concept that some of the phosphorus that we do supply and supplement as a fertilizer, we're not going to necessarily see back as a phosphorus source maybe in our lifetime. I mean, that's how long some of these materials are held on these clay edges. We get this labile phosphorus, which is, we consider this readily desorbable. And this is actually one of the fractions that we do measure within the context of soil testing. We get the single bonded oxygen. This can readily desorb and make its way into soil solution and satisfy crop demand. So what we're actually measuring when we're, let me go back a slide. What we're actually measuring when we're doing soil analysis, we're using a fairly acidic solution, usually going to be a Bray or a Malic 3. Malic 3 is slightly more acidic than a Bray. That acid is interacting with this clay edge. It's going to desorb some of this phosphorus that's available in there, and that's ultimately what we're measuring. And that translates into what you typically see on your soil test report, what we call available phosphorus. Okay. Just to give you a concept, this is an important idea when we think about phosphorus. This also sort of applies to potassium, but we don't typically use these. We don't typically use these types of models to describe this relationship, but for phosphorus, this is very important. So as we think about our goal as an agronomist, our goal is to maximize the amount of dissolved P in solution to satisfy crop demand, obviously within reason, because as I move up this chain of dissolved P, I run into greater and greater environmental risk. Where we actually want to operate is somewhere in this sweet spot, right, where we've satisfied all of the P sorption sites on the soil. That has resulted in a situation where I'm now increasing the amount of phosphorus that's ultimately in soil solution that's available to the plant. And that's where we ultimately would like to operate. Okay, that's where we want to be. As I dramatically increase the P that I supply, as I increase my loading of P in that soil, I get to the point where I can dramatically increase the amount of dissolved P that is ultimately in that soil that may be of environmental consequence. And this is typically what we see. I'm not throwing anybody under the bus. It's just a reality where we have a long-term history of manure application, and we have soil test levels. I've seen soil test levels as high as 2,500 part per million. Those are of environmental consequence because for the most part, we don't think that phosphorus leaches. And if you're maintaining an agronomic soil test level, it really doesn't to any great extent. There are some ways where you can sort of shunt the system that I'm not going to speak to today. Actually, I will when we start talking about transport mechanisms towards the end of this presentation. But ultimately, where we want to be is somewhere where we've satisfied a lot of those adsorption sites, so that as I supply just a little bit more P, I'm getting more in soil solution, so that the plant can ultimately take up more. This is illustrated very simply by what we call I could make this the red solo cup if anybody's familiar with the Toby Keith song. As I increase the amount that I'm loading, as I add more water into this system, notice as I add small amounts, the amount that leaks out, that's going to be synonymous with dissolved P. The amount that leaks out is fairly small, but as I increase the load, I have more and more holes where that water can leak out of that system. And as I dramatically increase the amount of phosphorus that I supply and satisfy a lot of those adsorption sites being these clay edges and mineral edges, I can dramatically increase the amount that leaks out into soil solution, and thereby dramatically increase dissolved P, which can be of environmental consequence. And typically what we do see, from my own experience, I've very rarely seen a farmer that's reliant almost exclusively on commercial fertilizers of having a soil test north of 80 part per million. I have just not experienced that much in my travels. Your experience may be different, but that's just what I've experienced. Where I really run into really, really high soil test phosphorus levels, it's primarily at a location that has a long-term history of manure usage. And typically those application rates are based upon a nitrogen perspective, and that's going to dramatically oversupply phosphorus. So just like we had for potassium, we've got this Bray soil test P. That's going to be our soil test level. Again, we're going back to this correlation between soil test level and relative grain yield. The one thing that you do typically notice when you're doing experimentation with phosphorus compared to potassium is we don't seem to have the same amount of scatter above the 100 that you tend to see with potassium. I'm not going to say that it makes the soil test phosphorus any more reliable, but we just don't seem to see as much scatter. It is maybe a better predictor of what the expected yield loss would be if you do fall below the critical. And we as academics have had this argument and continue to have these arguments quite a bit. What is considered optimum? I can give you my own perspective. What really, it's not so much how we describe it, it's really what the fertilizer decision is. If my critical level was 15 part per million, which is what this is what Iowa State uses, which is actually what University of Illinois uses. If my critical level is 15 part per million, if the recommendation is to never supply fertilizer above that 15 part per million, and we do have some folks that would promote that, that's a risky situation for me because I know that there are some observations above the critical where I do see some yield loss because of inadequate phosphorus supply. We're sort of playing a statistical game that I'm not going to drag you through this morning. So if we're using more of a sufficiency approach, I would get nervous that 15 part per million is my cutoff. With a lot of our land grant universities here in the Midwest, we use more of a build and maintenance approach. So as you approach the optimum, the recommendation defaults back to crop removal. So I'm less concerned with these qualitative classifications that we provide, that are provided. I'm more interested in, okay, what's the fertilizer recommendation for the farmer, for the grower? And again, some of this will become a little bit more evident as I move into a couple of slides when we start talking about rates. So this is ultimately what we're trying to do with soil testing, and this becomes the basis for providing us guidelines and recommendations for how much nutrient we need to be supplying to ensure that I'm not going to run into a nutrient shortage, whether it's phosphorus or it's potassium. So this is sort of a play on words. The name of the website that we manage is Economic, spelled with a K. We do know how to spell economic, but we are a primary potash producer, so we've taken advantage of that and taken some licensing. So the name of the website is Economics. So now I want to translate into taking that crop response information and actually generating a recommendation, which is ultimately what you're interested in. So just to give you a visual illustration of simplification of some of that scatter data that I showed you before. This is relative crop yield again, and I've got soil test K level, and this is essentially what it looks like when you sort of get rid of some of the scatter. Now this is the average response function for Illinois and Ohio with regard to soybean, and the critical level in Ohio was somewhere around 120. They're somewhere just north of that, 125. Illinois is fairly similar based upon my reading of the University of Illinois recommendations. So now the question becomes, if this is the relationship between soil test K and relative crop yield, now I have to go in and do some work and say, okay, at 100 part per million soil test K, how much fertilizer do I have to supply? That's ultimately what you're interested in. Just to show you what the crop response curve for phosphorus looks like, I've got Iowa, Illinois, and Ohio. And the one thing that you notice is when you look at the data that's aggregated across these multiple geographic areas, they all sort of look fairly similar. And that's not necessarily too surprising because the soils that we're farming in Ohio are not all that dissimilar from Illinois, although I would venture to guess that a lot of our Ohio farmers are fairly jealous of the soils that you do farm in Illinois, and I just realized I misspelled Illinois. So for a lot of our soils, the critical level is defined as about 15 part per million. If you notice the crop response functions, if we're going all the way up to about 100%, it's probably going to be closer to 20. Again, I get less hung up on what the actual number is, and I'm more interested in, okay, what's the fertilizer recommendation at these soil test levels? That ultimately tells me whether or not I'm going to be risking much on the farmer's behalf when it comes to making a rate decision. So just taking that a step further, so we have a range of soil test levels. This is probably going to make a little bit more sense. I do apologize for the amount of text. Here's the K recommendation that's provided as far as a guideline from the universities. Here's the adjusted yield loss. Now, I adjust this spatially. I'm not going to dig into that model and how that actually functions. But this is the yield loss that one would expect. It's not a guarantee, and this is not the worst case scenario. This is the average yield loss if you're farming a soil at this soil test level. You can expect at least a 40% yield loss on average. The probability of seeing a response to a fertilizer application rate is fairly high. I like to joke about this and say if I could guarantee you a 95% probability of a win, if you went to Vegas today, how many of us would jump on the plane and make that trip? My suspicion is quite a few of us. And notice as your soil test level increases, the K recommendations do decrease. The yield loss due to inadequate K supply decrease, and the probability of response also decreases. So this is just a visual way of taking that crop response model that I've shown you here and actually translating it into meaningful numbers. And again, some of this comes right out of the University of Illinois handbook for fertilizer, and what they provide is guidance. And then some of this is some of the models that I've built based upon a spatially adjusted yield loss. And again, I'm not gonna drag you through how that actually functions. Phosphorus looks fairly similar. Again, at very low soil test levels. Sorry, that should say P, not K. The P recommendation at that soil test level. Here's what you would expect as far as the yield loss if I didn't fertilize, or what I would expect as an average yield gain if I did. And here's the probability of response. And again, notice as my soil test level increases, and that should also be P, as I increase my soil test P, my recommendations go down, my yield loss goes down, and the probability of response goes down. Now, the one thing that you have to understand, and this is very important for you as an individual, as a consultant working with the farmer, is there's always some level of uncertainty in the information that we capture from soil analysis. So the one thing that I always stress when I talk to individuals about soil testing is make sure you're collecting an adequate number of samples to represent the area that you're basing a decision from. And the reason I say that, because this is a real world scenario. I got this from Bob Miller at Colorado State University. This would be like a grid point sampling approach. So this is where my grid point is based upon my Latin lawn that I've overlaid across the field. This is a 10-foot radius, 20-foot in diameter, and they went in there and they poked 12 different holes, obviously with a slightly larger bore for the core than traditional, not the traditional probe. It's a little bit larger of a bore size, so they get enough of a sample that we can actually do analysis on each one of those individual samples. So each one of those individual samples are represented here, the 12 holes. The soil test K for those individual cores that were collected ranged from 81 to 162. So if I came into this location and only poked one hole, my potential information would tell me that I'm fairly deficient with regard to potassium, or I'm fairly sufficient. And this is the type of variability that we do observe in the field. And again, I can walk you through why this is. Some of this it relates to the way we fertilize using primarily spinner spreaders. Some of it has to do with our harvest operation. Some of it is related to tillage. This is obviously a minimum tillage system. But there's a lot of potential sources of variability that contribute to this fairly wide range if I don't collect enough samples to adequately represent this area. So this area, the average is 110 or 112, but if I don't collect enough cores, I'm not going to get an accurate representation of what that mean is. That's critical. This is just this is me doing some statistical gymnastics. If I only collect 2 samples, I do narrow my potential error slightly. As I increase the number of samples, my potential error gets smaller and smaller. This is also part of a justification for why we say you should collect as many soil cores as we do recommend. Typical recommendation says, I usually say 15 or more. I know that can be cost prohibitive when you're talking about a more intensive grid-based or some sort of a geospatial sampling approach. But there is a reason we do say you need to collect a certain number of soil samples. There's justification for that. We're trying to minimize the error associated with that measurement. So just to show you one more thing, and again, I usually have a lot of slides that lead up to this, but in the interest of time, I don't have that this morning. when we represent a single value, so this represents a population of soils that were collected. The average is 18 part per million from this particular population. So if you're looking at that relative to what the critical level is established in a lot of our Midwestern states, which is close to that 15 to 20, if it's 15 part per million, we would consider that an optimum soil test level. Well, let's dig in a little bit more. We've actually done spatial analysis of this soil, and it turns out if 18 is the average, 42% of the population that goes into constituting that average is below the critical. And I'm hopeful that that is somewhat intuitive, that if the mean is just a representation of the average for the population, and there's going to be a bell-shaped distribution that goes about that mean across that population. And this is where I start getting very nervous about saying, well, the critical level is 15, so at 15 part per million, our recommendation should be 0. Well, if your critical level is 15 and the soil test level comes back at 15, the inference should be that there's a considerable amount of that population that's going to be below the critical. So what I've argued for those who are going to employ more of a sufficiency-based approach, where as soon as you hit what they consider the critical level or the optimum number, the recommendation goes to 0. I've argued, well, then you should probably shift your critical level considerably higher so that you don't run into that situation where a farmer whose soil test says he should be good, well, it turns out a lot of his soil would not be considered good based upon the critical. So we can make a mathematical adjustment and deal with that. And then when it comes, so what I shared with you before about the spatial soil analysis, I've actually taken this into account when I'm taking small plot data and translating it to the field scale. This is an important part of this whole discussion as it relates to soil testing. Is there is some uncertainty. So now what we've done is we're taking those agronomic models that we've developed for potash and for phosphorus, and now we're just going to translate this into an economic model. I've got soil test level here in the first column. I've got what the potassium recommendation is, what the yield response is, the average yield response. And again, I'm not taking this to the highest degree. This is not like a marketing campaign that says you can see a yield response up to. This is the average yield response based upon the crop response models at that soil test level. We have the cost of fertilizer to make that potassium application rate, the revenue generated at the yield level, yield expectation that we have for this soybean crop at 60, and this is the return per acre in dollars per acre on that potassium investment. So the point here is it is the expectation of return is a function of the yield that is achievable. And this is why it is so important to manage other agronomic factors to maximize yield potential. So for the 60 bushel crop, $300 a ton potash, $9.85 soybeans. Notice as my soil test level creeps up, what happens to my expected level of return? It does decrease. If I made that next incremental step and went to like 200, the return per acre would likely turn negative. I have that in the phosphorus discussion. We'll talk about that just a little bit more. So if I can increase my yield expectation from 60 to 75, what happens to my expected level of return? It obviously increases. Notice the revenue generated doesn't change because we're ultimately trying to hit the 75 bushel or the 60 bushel per acre yield. So my revenues are all going to be the same. It's just how much return on the investment in fertilizer am I going to be generating? It is a function of yield. That's an important consideration. That's part of the reason for the title. So for the phosphorus, we're going to basically do the same thing, building that economic model. Here's your soil test, your range and soil test levels. I apologize. When I was putting this together, apparently I wasn't paying too close attention to making my adjustments between phosphorus and potassium. That just tells you that this is a brand new presentation that I built yesterday. Here's the expected yield response, average yield response. Here's the cost of fertilizer. Here's the generated return. Notice as I go from 60 to 75, as I increase my yield potential, what happens to my expected yield or my expected return on the investment in fertilizer? It goes up, and hopefully that's intuitive. The one thing I do want to say about this -3, is that a good or a bad thing? And as a recovering academic, the answer is it depends. And it primarily depends upon the cost of fertilizer in the future. So if we think this $400 a ton for MAP is a good buy and our expectation is that fertilizer prices in the future are going to go up, what's the right decision economically to be made to invest in slightly more phosphorus for this growing environment and be able to take advantage of what I've supplied today and decrease my need for future phosphorus with subsequent crops. So whenever you see negative numbers, it's not always a clear cut that this is a horrible decision. It may not necessarily be. Okay, so we've talked about economics, and those are probably the most important slides, to be honest with you, within the context of this presentation. Fortunately, these are going to be available through the website. I know I didn't spend as much time on these as I potentially could have, but in the interest of time, I'm just going to have to move on. So when we start thinking about phosphorus mitigation and managing loss pathways, I'm going to assume that everybody understands how soil erodes. And the only reason I'm going to operate on that assumption is my suspicion is we all have some level of experience with high rainfall events and in a conventional till system, and we can see where I have any sort of appreciable slope, I get sheeting or some sort of a real erosion, and that's the physical transport of soil offsite or to at least to a lower position within the landscape, or potentially to the edge of a field. It ends up in a drainage ditch. The drainage ditch fills up with sediment. Okay, when that is occurring, that is transporting what we call particulate phosphorus. Some of this is just to help you with the language and the lingo that we use to describe these different fractions of phosphorus. So for dealing with particulate P, we have a pretty good approach to managing particulate P, and that is conservation or no-till. And that's very, very effective at mitigating particulate P transport. The one thing that I do have to say about particulate P, whenever it hits a water body, at least from the environmental perspective, it's not 100% bioavailable. That is important. So whenever we get sediment transport, it winds up in a water body. All of the phosphorus that was moved into that water body is not available for a aquatic plant species to grow and utilize as a nutrient source. In fact, it turns out it's only about 30%. So from an environmental perspective, I'm much less concerned about particulate P because it doesn't cause as much eutrophication in the water body that's going to ultimately negatively impact that water body. Now, are we concerned about sediment transport from an agronomic perspective? And the answer is yes, because if we continue to have sediment transport, that means we're losing topsoil, we're losing productive soil that's got organic material. That's not the best case scenario. We would like to manage our production system to mitigate the risk of sediment transport, which is going to transport that particulate P fraction. Now, there's another fraction of phosphorus that we have to deal with, and that's this dissolved phosphorus. Now, I'm going to assume here at the very beginning there's no recent fertilization. That's going to go away as I start getting into some of these qualifiers. So dissolved phosphorus requires desorption or dissolution to provide solution phosphorus. Okay, this is the phosphorus fraction that ultimately can be utilized by a plant. This can and does occur. We know this because even if we don't supply any fertilizer, if I went back a few slides, your yield at a soil test level of 1 part per million, which I've never seen, the lowest I've ever seen is 3, the yield at a 3 part per million soil test phosphorus is not 0. Yield is something that maybe is 50 to 60% of what I could ultimately produce. Okay, so that there is some level of desorption and dissolution occurring in that soil. So some of that phosphorus can be transported. Okay, and now for typical soils, the amount that's lost is fairly small, and that'll be fairly apparent as I get into some of the data slides. There are exceptions. Okay, the exceptions are: have I had a recent fertilizer application? Specifically, have I had a recent fertilizer application, whether that comes from a commercial fertilizer source or it comes from manure that's not incorporated? So it's sitting on the surface of that soil awaiting a rainfall event. That material is at risk, and that'll be fairly evident here in a couple of moments. No-till systems with extreme stratification of phosphorus into the soil surface. I have done some work on worked with some farmers that have been involved in no-till for 15 to 20 years, and if you do some level of stratification of the soil analysis, you can find that that top 2 inches has a lot of phosphorus. The top 8 may have a soil test phosphorus level of, let's say, 20 to 25 part per million, but that surface level, that top 2 inches, can be as high as 80 to 100. And that relatively tight environment, that top 2 inches, I'm going to be seeing more dissolution. I'm going to be seeing more desorption because of the mechanisms I've already described. And in that situation, I can see you do have an elevated risk of phosphorus surface transport in that production system. And then I can also see this with soils that have excessively high soil test levels. And again, that's primarily going to be where we're managing manure or organic inputs into that production system. Here's the bad thing about dissolved P. Unlike particulate P, which is only about 30% bioavailable, dissolved P, whenever it hits a water body, it is 100% bioavailable. So some of the areas where we have eutrophication issues that result in hypoxia or oxygen deprivation, a lot of this is going to be driven, or all of it's going to be driven by the bioavailable fraction. And dissolved P is 100% bioavailable the day it hits the water body. Particulate P does not. So the question becomes, how do I manage these two different loss pathways? So to mitigate particulate P, no-till conservation tillage, maintaining some sort of a cover on that soil to decrease the energy of the rainfall as it impacts the soil, that's a really good way of mitigating that risk. That doesn't necessarily help me on the dissolved P, because there's always going to be some level of surface transport. So just to give you some real experimental data to substantiate some of these perspectives. This is a phosphorus loss from an experiment. I can't remember where this was actually conducted. I've got triple super, I've got low manure, I've got high manure. This is 1 month after the application. So the 1 MO represents 1 month. I've got dissolved reactive phosphorus. Then I've got 6 months. And what do you notice about 1 month triple super? I get a fairly large rainfall event, and it's not incorporated. This is a surface application. My loss is fairly high relative to where I incorporated it with a chisel plow. Okay, so if I do some level of incorporation, I decrease my dissolved P load. What would you expect, however, would be the case for the particulate P load. Okay, where I do tillage, I'm most likely going to have a higher particulate P load. And this is the rub that we have with phosphorus management. I'm trying to manage two different pathways, and the right answer for both pathways is not necessarily the same. Okay, so we're going to have to come up with some sort of a hybrid. But one thing to notice, and this is critical as it relates to timing of fertilizer applications. If we can make these applications at times when the risk of high rainfall events are relatively low, so that it's just like managing urea, the ideal situation would be I make the application today, and then it starts raining, let's say 48 hours later, but it's not a large enough of a rainfall event that generates surface transport. I'm getting enough to dissolve any fertilizer material at the surface. It's going to move it just ever so slightly into that surface, interacting with the soil. And then over time, what happens to the benefit of incorporation? It starts to go away. It's still there to some degree, but it's certainly not the magnitude that we experienced with a relatively quick, large rainfall event that generates runoff. Time is to our benefit to ensure time away from large rainfall events ultimately. So if you look at some of the guidelines and some of the laws we now have in Ohio with regard to how we manage fertilizer inputs, one of the guidelines is we're not allowed to make surface applications if the expectation is a half-inch rainfall event within the next 24 hours. And part of that is motivated by this particular data. Just to give you a really quickly, just to illustrate the point again, this is tillage regime. I've got a broadcast application. I've got the check, and then I've got a knife. The check received no fertilization. Then I've got a knifed in application. I've got soluble P load. Application rate is 55 pounds of phosphorus per acre. Where I chisel that material in, what do you notice about the risk specifically compared to a broadcast application without incorporation? Much higher risk of transport where I'm putting that material on the surface and exposing it to the surface runoff pathway. Now, again, I'm not showing the particulate data set. This is this is the particulate P, so this is the total P load. And so what do you notice? The soluble P, we have a huge advantage where I do chisel or some level of incorporation. But what happens with the particulate P? Well, because I am doing tillage, I do start to lose a little bit more phosphorus when I'm specifically looking at the check compared to the no-till compared to the tillage. Again, the point is, ideally, we want to somehow get that phosphorus application to interact with the soil. Ideally, that's what we're trying to do. It doesn't necessarily have to be tillage per se, but some level of incorporation That's ultimately what we want to shoot for. There are some individuals that propose bringing back moldboard plows. That's not my perspective, because they're going to dramatically increase particulate P transport. So somewhere there's got to be a happy medium. This is just some of my own work at Ohio State, looking at, again, P load, whether it was incorporated or not incorporated, and then looking at the two different fractions. This is the best illustration I have. So if I incorporated that material, notice my soluble P load is about 4 times lower than where I left it on the soil surface. But where I did do tillage, what happened to my total P transport? It was higher. Okay, this is trade-off that we're somehow going to have to figure out. I'm going to skip the next slide because it's basically showing the same thing. And I want to conclude here, and I know I've sort of pushed Dan on time here, and I apologize for that. This is a study that was just recently published. Some of these, this should be ammonium polyphosphate. I stole this from their presentation, from their publication. Not ammonium, not polyammonium. It should be ammonium polyphosphate. Relative loss percentages, these are fairly high. So what we typically see, so some of my own work where we've made surface applications of phosphorus and then exposed it to runoff. I mean, we actually generated the runoff ourselves. We had a rainfall sprinkler, a rainfall system there. We're purposefully making it rain so that the precipitation rate exceeded infiltration, so we were generating surface movement of water. We're typically talking about percentages of less than 5%. Now these are fairly high. As I dug into the literature, the other highest one I saw was 15%. So that means that 15% of what I've supplied was lost. That's really high. Typically, my own work was less than 2%. But it still illustrates the point. If I'm surface supplying, the load loss that I'm going to occur is fairly high. If I can band it, okay, so I've got map and map. Where I can band it, I dramatically decrease the loss potential. When this is banded, this could be made as a starter application. There's a couple different options. This could be a strip tillage application. There are some alternatives to just a strict band. There's multiple ways that we can achieve this. Interestingly enough, from this data set, and I'm not necessarily sure that I can describe this, but the poly source that they used, which is obviously a liquid material, didn't experience as much loss. Could that be because of better interaction with soil using a liquid compared to a dry? Potentially. That's what they described within the context of their experiment. It could also just be a result of the analysis, and I haven't found any other publications. When we're supplying poly, 25 to 30% of that material is in an ortho form, which is what we're actually measuring when we're measuring dissolved reactive phosphorus, or DRP. The polyform wouldn't show up because that is not an orthophosphate. That's a bunch of orthophosphates stuck together. So I don't know if this decrease in load is because of better interaction with soil or just an artifact of the way they conducted the analysis. But it's sort of interesting that a liquid application might represent less risk of transport than a traditional dry. I'm going to reserve making judgment on that until I see some better data, because I do sort of question the analytical approach that they employed. So when it comes to mitigating, and you notice I didn't talk anything about potassium as it relates to mitigating nutrient losses, and it's not to say that it's not important. Environmentally, to date, we don't have any consequence of excess potassium transport. Again, from some of our own work, the amount that's actually lost is fairly small. So with that surface application, the potential loss is again, from my own work, was less than 2%. There's some other work that may say that that's maybe closer to 10. Agronomically, that's not that big of a deal. If we start encroaching closer and closer to 20% now, it really starts to pencil out economically. But for phosphorus, we're trying to manage these two different fractions. Conservation, if we're managing particulate P, conservation tillage, no-till does a really good job of managing that transport pathway. It isn't necessarily our friend for the dissolved P pathway. One thing that we've really started to promote is somehow we've got to get that phosphorus below the soil surface to mitigate the risk of transport. And traditionally, that's been a surface application with a spinner spreader, followed by some level of incorporation with tillage. It doesn't necessarily have to be that, though. starter applications of phosphorus, strip till applications of phosphorus are going to have a much lower transport risk. And then how does this relate back to soil test levels? If I'm managing my soil test level, let's say somewhere above that critical, somewhere in that 20, 30, I've even gone so high as 40 part per million, and I'm managing my phosphorus inputs to minimize dissolved P transport while also trying to account for particulate P, the environmental impact of our operations is going to be managed to the best of our ability. There's still going to be some loss, but we're at least going to be minimizing what the potential environmental impact of what we're doing within the farming operation. And I feel like I just turned on the water hose and let you take a drink. We do have about 5 minutes. I do apologize, Dan, for going over about 10. Covered a little bit more information than I thought I was going to be able to cover, but if there are some questions, please feel free to ask.
All right, Robert, thank you. A lot of questions here.
That's good. That's what we want. I don't know if I have any answers.
I will try to go through some of these things. I'm not sure where to start. One of the things, I'm going to start with a question I had. You talked about absorb P, dissolve P, and you want to be in that sweet spot, this zone. How does a farmer know where he's at? Or a CCA for that matter? Yeah,
so analytically, I'll slide back to that slide really quickly. I'm probably driving Chloe crazy. I'll slide back to that. So we actually do have ways of measuring P sorption. It's not something you would ever see in a traditional soil test, though. And part of that is it's primarily dictated by cost. But we do have that capacity. The way I would think about it is if you're managing your soil test somewhere close to the critical level or just above, you should, my humble opinion and the data I've seen, you're never going to get to this point where you're going to dramatically increase the dissolved P fraction. My own guess is if we're managing at the critical level, we're going to probably be somewhere right about here. If you can see where my pointer is. This is sort of reserved, again, I'm not throwing anybody under the bus. It's just a reality. This is usually the animal operators that are transporting manure to the same field year after year after year. But for those of us that are managing commercial fertilizer inputs, we tend to be somewhere right about here. If you're interested, I suspect that most labs could actually do a P max analysis, and it should theoretically be somewhere above our critical level.
Okay. Okay. The fact that you're right, if we're managing phosphorus for the crop using commercial fertilizer and not manure, I think you're right. We're going to be okay. I think that's your point.
Yeah, it's really expensive to build your soil test level up to 2,500 part per million with commercial fertilizer. I can't imagine many people could afford it.
No. Okay, let's go to some other questions. You talked about this dissolved P transport. Loss and runoff. Well, out of Ohio, they've been talking about using gypsum, calcium sulfate to remediate that.
Yep.
Can you comment on that?
Yeah, that's gained some popularity. Does it work? To some degree, yes. And the basic idea is surface application of P. I'm going to supply some gyp, which the reason we wouldn't select lime is because lime is terribly insoluble. Not that gypsum is that much, it is 10 times more soluble than lime, but that's not saying a lot because lime is really insoluble. Gypsum has a little bit higher solubility, so the idea is at the surface where I have that free phosphorus as that fertilizer granule is dissolving, I'm going to also be leaking some calcium. The calcium is going to bind with the phosphorus, so it's going to decrease the risk of transport. There is some data that substantiates at least some of that claim. My concern is that's not a long-term fix, and it's also a fairly expensive way to manage P, because now I'm going to have to incur the cost of the gypsum application as well. There's also some data, and I've tried to find this. I saw it at the national meetings. What was it? 2000? It would have been 2016 in Phoenix, where there was some work out of Minnesota where they were using that approach, and what they were learning is that calcium tie-up of the phosphorus is ultimately impacting availability of phosphorus to the crop, which it makes sense, right? If I'm dumping on calcium, trying to precipitate out phosphorus. Well, if I'm precipitating out phosphorus, I'm decreasing the phosphorus that can resupply the phosphorus in the soil solution. So they were actually recommending that you needed to apply more P in that situation, which seems kind of counterintuitive. Does it offer some opportunity? It does, but I'm not sure that's necessarily the best approach.
Okay. We're going to take a few more minutes here. We're going to go another 5. It's totally okay.
Okay.
I'll let you, what is your experience of 2-year corn, soybean fertilizer applications? That means 1 application in 2 years versus annual applications per crop. What's your experience, your recommendation on that?
Yeah, great question. So I actually established a study in 2005 looking at that very thing, Dan. Now, in the context of my study in Ohio, the common approach is we're going to fertilize after beans, and we're going to usually put on enough based upon our experience with yields for corn and beans to satisfy both crops in that rotation. Has it worked? I think it works fairly well. Is there some opportunity to capitalize on fertilizing the beans directly? So instead of doing it every 2 years, maybe going every year with that application. There's some other data out of Kansas State. It was just presented at the national meetings down in Tampa, where there was a young researcher who was reporting some benefits to directly fertilizing the soybean, specifically on the phosphorus side. I don't think K was involved at all in the study. So are we potentially losing out on some yield by not directly fertilizing the beans and just supplying enough P and K prior to corn? And then I don't like the word. I know we sort of call soybeans a scavenger crop. I really am not a fan of that because soybeans are just as responsive to P and K as corn is, and in fact, maybe more so in certain environments. Can you get away with every 2 years? Yeah, it's really a function of soil tests, Dan. From my own experience, if I'm maintaining a soil test level, let's say the critical in Ohio is 15 for phosphorus and 125 for potassium. If I'm somewhere in that 160 to 170 K, somewhere in that 25 to 30 for P, I think that every 2 years is okay. But if you're sort of straddling that critical level, that might be the situation where you might need to be directly fertilizing those beans and not just relying upon that 2-year rotation. There's a lot of factors that go into that, but the work that she was presenting was on a fairly low soil test, just below the critical level, and I think that might be the deciding factor. But that's sort of an educated guess on my part.
Could you? I'm going to do several more questions here. These are good questions. Which is more important than soybeans, P or K? And if you follow Dr. Fred Below's 6 secrets, he's concluding that farmers need to be paid more attention to P probably than K. But we know that soybeans have a higher K requirement than corn does.
Yep.
But the secrets say has us focusing more on phosphorus now. What are your thoughts on that? What's P and K?
So I know Fred, and I like Fred. Fred and I have a really good relationship. I'm going to disagree with Fred here. There's got to be some context, right? So it depends. If my soil test is going to be somewhat of a dictator of that. So if my soil test P level is really low and my soil test K level's relatively good, obviously the most important factor to me in that situation is phosphorus. I've got to make sure I increase phosphorus supply to that crop. If they're both adequate, I don't necessarily know. Maybe from his own data, that's where he's sort of. I think that's where Fred is sort of gravitating towards P. Is if they're both considered relatively adequate, that P nutrition becomes a little bit more important. From my own experience, it wasn't actually from any of my research. It was one of my predecessors at Ohio State University, where if we had low soil test P and K, I actually have several locations, I'm going to get this wrong, and I apologize. I want to say 7 out of 12 crop years, if I supplied P without supplying K, I would actually decrease yield. I never experienced that if I increased K but didn't supply P. So at least from my own experience, if both of those nutrients are considered deficient in the soil, K is the most important factor. Now, I'm not the only one that observed this. Kerry Lebowski has just completed some work. It's not published yet. I think it's available through University of Wisconsin's website. It's actually on our website as well, potashcorpeconomics.com, where her data sort of matches with what I've experienced in Ohio, where if they're both low, if my soil test P and my soil test K level are both low, I see a much more dramatic response to supplying K than I do phosphorus. So in our situation where they're both low, and this may be the differentiator from what Fred is saying, if they're both low, K seems to be the more important nutrient, the one I need to be focused on initially. I'm not going to say you don't need to supply P, because our approach as an agronomist is to, I want to remove all yield limiting factors. So if my soil test P level or my soil test P and K level are both low, they both need to be supplied, okay? But the expectation is, from my data and from Kerry's data, and actually Antonio has some data that would substantiate this as well, it's not as clear, is that K is, if they're both deficient, K is really, really important. And again, that sort of comes back to our campaign of going from NPK to NKP. And there's also some data on alfalfa from Jeff Valenick out of Purdue that shows the same thing. Again, I don't like to play the game of which one's more important, because if they're both deficient in soil, they both need to be supplied. But I've had that question, as I'm sure some of the consultants maybe sitting in this audience have had. They're both deficient. I've got limited resources. Which one do I invest in? I hate to play that game, but in all reality, should be splitting the difference anyway. But K, from my own data, seems to be pretty important.
Okay, one more question we'll do here about P and K placement, strip till, and rates. There were several strip till questions about P and K and placement and rates. Can you just kind of talk on that?
Yeah, so sort of the traditional approach is that if I can make a banded application of, we've really focused this on phosphorus. It really hasn't impacted K much, at least from my own experience. But at least on the phosphorus side, the idea being if I can band the application, minimize the soil interaction between the fertilizer granule and the soil environment, I can have an efficiency that I can take advantage of, so I can actually cut back on my rate of fertilization in that banded application. Same applies to starter. And there was some data published, I think it was published back in the 60s, that actually illustrated that point fairly well. And they had sort of concluded, well, from their research, there was a 50% improvement in efficiency. And again, it comes back to the fertilizer granule as it's dissolving and interacting with soil. We're getting all this adsorption, we're getting all this precipitation. If I can create this phosphorus-rich environment, I can sort of satisfy the local adsorption and precipitation reactions and increase P supply in that really, really small zone. And when the plant root hits it, bam, it's got enough to supply its needs. The more recent research that I've seen, Tony Vine's doing some of this work out of Purdue, Antonio's done some of this work out of Iowa State University. I even think that Fabian Fernandez had done some of this work, and he was at University of Illinois. I don't know that 50% is the right answer. I think that's a little bit high. From my own experience, maybe 10 to 25%. 25% might actually be a little bit high as far as an improvement in efficiency. So I can cut back just a little bit, because I am improving the efficiency of the performance of the fertilizer that I'm supplying. The challenge becomes I can't continue to do that long term, because ultimately I'm going to start dragging down my soil test level. It's just going to have to happen. It's simple math. But you can capitalize on some of that efficiency with a banded application, and that would certainly apply to a strip till.
That's mostly, I think you said up front, mostly that applies to phosphorus. You really don't get that benefit from potassium.
That's correct. I've never seen anybody talk about this from the potassium side, and it's all because of the way potassium behaves in the soil. But phosphorus, there might be some opportunity.
Okay. Well, it's Robert, Dr. Mullen, thank you very much. I'm going to forward these questions to you, and you can look at them and things. Very interesting questions. Okay,
I'm sure this is a lot of data. Thank you for your time. Thank you so much, Dave.
Yeah, thank you, Dr. Mullen, for giving this great presentation. Very, very, very informative. Lots of good materials. Again, just to wrap up, if you sign up and participate in today's webinar, and gave you a CCA number, you will get a credit in nutrient management. If you're listening to the recorded version of this, you can go back online in your CCA account and self-apply for a credit. Again, on behalf of the Illinois Soybean Association and also advisor of Soybean Management website and Potash Corporation for letting Dr. Mullen do this, I want to thank you for attending today's webinar, and this webinar is now done, and I wish everyone a good day.